All right, we are recording. So thank you all for joining for the last lecture of this long journey for the first ever workshop of AI for People. I hope you enjoyed the previous lectures as well as the invited talks. We are here for the last lecture, which is going to be about continual learning for AI, the last advanced block 4. And I'm going to be introducing this topic to you. My name is Vincenzo Lomonaco. I am a postdoctoral researcher at the University of Bologna, working on the same topics. And so we'll be taking an hour and a half for this lecture. It is introductory, and I hope you follow especially the Kevin's introductory lecture to PyTorch, so that we can also have an hands-on session where we will use PyTorch to try to implement some algorithms for continual learning. So before starting, let me just say a few more words about myself. Other than being a researcher at the University of Bologna, I am the president and co-director of research at Continual AI, which is another nonprofit research organization, which is working specifically on these topics. If you find that interesting, I invite you to check the organization out at the official link from continualai.org. And why not joining our Slack and talk with more than 900 researchers that are now working together towards this very nice research topic, which is currently getting more and more attention inside the AI and machine learning community. So other than that, I've been working for a long time now as a teaching assistant for the courses of machine learning and computer architecture at the University of Bologna. And I've been also the author and technical reviewer, respectively, for the Deep Learning with R and R Deep Learning Essentials books. And then finally, the co-founder and board member of AI for People as well, and the organization which is presenting this workshop to you. So without further ado, let's jump right in the lecture, this workshop or lecture about continual learning for AI. So what we are going to see today is an introduction to continual learning. So what it is and why it is useful, why it is important for the future of AI. And then after this introduction, which is gonna last around 20 minutes, we are going to work on a notebook that the Continual AI community created, and we have adjusted for this particular lecture on this workshop. It is an hands-on session that as the only prerequisite is as essentially a basic notion of machine learning and PyTorch that is already being presented by Kevin in the a coding AI lecture, and is going to be a gentle introduction to continual learning in PyTorch 1.6. That is the latest stable version of PyTorch. So then, depending on your level of proficiency, it's going to take like from 40 to 60 minutes to complete that part. And then if we have time, we will address some let's say, latest research and the resources that are available for continual learning, as well as trying to understand where continual learning can be applied inside an unsupervised learning context, a reinforcement learning context, or on real-world applications in various scenarios. So let's start with the introduction. So as many of you know, deep learning holds state-of-the-art performances in many tasks in computer vision, natural language processing, speech recognition, and all the downstreams applications. This is mainly due to supervised training from, I would say, huge and fixed data sets collected a priori, right? However, no matter how big our training set is, as we grow in terms of data dimensionality, and we would like to tackle more and more complex problems, it becomes exponentially harder to collect enough data that can represent the entire space of possibilities we would like to tackle, right? especially when mixing multi-domains, language models with vision models, and so on and so forth, trying to get to that level of intelligence we would like to see in our agents and systems. And I mean, this is complex, as you can see also from this big number on this slide. That is the number of possible images you can create from a small patch, a small image 227 for 227 pixels, so a very small image. You can find all these possible combinations. So it's a very huge space of possibilities you would like to tackle in a symbol, for example, computer vision problem like object recognition. It's a huge space you would like to cover with just a data set that cannot be somehow fixed and collected a priori. And this is an example of the problems that can arise otherwise. So in these 4 images, essentially are 4 different images that maximize the activation of the neuron corresponding to the Barber class of a pre-trained neural network on ImageNet, so on more than 1 million images. And I think that this was covered by Gabriele in his talk on creative AI. Somehow, essentially, these images are somehow created to contain the features that excite the maximum level the response of a neural network for a particular class, in this case, the barbell. And as you can see, the network has somehow a biased understanding of the barbell because it also contains people arms. So it clearly means that we have not collected enough data, enough information to cover that particular sub-volume of the entire space of the barbell class, right? So we have just seen link training a lot of images containing both people's arm and as well as the barbell. So in the end, the network has a very biased understanding of it. And this is happening everywhere. I mean, in fact, you don't need to be confused. High performance in terms of accuracy doesn't mean that the network has not a biased understanding of the task he's trying to solve. And you can find these possible mistakes and misunderstanding all over. In fact, there's also a say in machine learning and statistics that every predictive model is somehow biased, and you can do much about it. It's the very nature of a predictive model, try to model the world with an approximate level so that you can also generalize the situation you have not encountered yet. And then this is another example with a captioning neural network where this image of a flooding is described as a group of people standing on top of a beach. And even in this case, it's clear that we have not collected enough data, and in this case, images and caption pairs to describe accurately any situation of a flooding. It is not that common. And of course, this particular subspace of captioning is not well covered by our data. And hence, these are 2 important examples, for example, of situations in which it's clear that even though we have very big data sets, we have not yet been able to cover the space in a way that is somehow unbiased. And I argue that it's clearly impossible, and it's at the heart of the curse of dimensionality. It's what is being called. And how then can we still improve AI scalability and adaptability? How can we scale in terms of intelligence while getting more and more data, and how we can adapt to new situations we have never encountered before, and how we can be more ubiquitous and autonomous in terms of AI systems? And the answer to us and to many researchers is continual learning. So we would like to move away from this very rigid paradigm of training offline and then deploying the model of AI system with frozen learning capabilities, and rather move away from, and move towards a smoother way of learning where we constantly update our biased understanding about the external world, always improving and generalizing over time, and essentially exploring this huge space of possibilities that we like to tackle only locally and during time. And this is the only way you can make an AI system sustainable over time as well. And so practically speaking, in terms of mathematics, as we learn a particular mapping function, f of data, our neural network, our model, from the x1 to the y1 distributions. Then as we encounter a new couple of distributions, x2 and y2, what we would like to do is to somehow generalize this model to handle both mappings, but without accessing anymore the data that we encountered before belonging to the x1 and y1 distributions. Continual learning is the only, I would say, higher and realistic, paradigm that can let us deal with an higher and more realistic time scale where data and tasks become available only during time. So there's this critical notion of time that is not just embedded in the patterns that we are trying to analyze, but also the idea that time somehow has an impact on machine learning systems, because you can't have all the data available at once when you start. And so another important property is that you don't have access to previous encounter data. Hence, you can be constant in terms of computational and memory resources that you deploy for your AI system, essentially acting as a filter of the world of perceptions we are in as our brain, and incrementally developing even more complex knowledge and skills. So why continual learning is then challenging and interesting problem from a scientific perspective? Well, it turns out that the connectionist models such as neural networks with gradient-based optimization suffer from catastrophic forgetting. So essentially, when they are trained on a new data distribution, on a new piece of data, they suddenly erase the knowledge encoded in the weights of its model in favor only of these new distributions, or completely forgetting the past. And this is also well known for biologically learning systems, and as the stability plasticity dilemma, that it's that says that it's quite complex to gain new knowledge from the world and being plastic enough to somehow encode this knowledge in our models or in our brain, and at the same time preserve the information we have already collected about the world. And it's a trade-off where we need to figure out how to do at least as well as the human brain. So in this slide, you can see an example of catastrophic forgetting, or also known as catastrophic interference, in a standard computer vision object recognition scenario, in which we encounter a number of training batches over time, containing different classes. So in these objects. In this slide, you can see on the x-axis the number of encountered batches with five different objects that we need to learn to recognize over time. And as you can see, the accuracy curve here is flat. That is, as soon as we learn a particular bunch of new objects and we learn to recognize them, we completely forget how to distinguish the previous ones. And you can tell that also by looking at the confusion matrix, the evolving, let's say, confusion matrix on the right, where these vertical bands essentially indicate that we are actually guessing only among the newest objects, the newest class we have learned from. So in the last few years, I guess from 2016 or around that time, we have seen a renewed interest in tackling this problem and make somehow, especially neural networks, work in an incremental learning, continual learning setting. So I'm not going to go into details about all these different strategies that have been proposed and algorithms, but I think we can conveniently frame all these categories in three different parts, or four, it depends on how we can see them. Then the first one is the regularization category, in which we can find all the algorithms that somehow try to regularize learning and the optimization process, so that they can preserve the weights that are important for the previous data distribution while learning about a new data distribution. And then the architectural category, in which all the methods are now based on architectural changes in the structure of the model, the neural network. For example, freezing some weights, adding neurons, adding connections, and changing the structure of the network. And then another category is the rehearsal one, which is somehow based on the idea of allowing an external memory to exist, in which we can store patterns that are representative for the previous data distributions, and then use these external memory to be somehow mixed with the new data, and somehow learn from this mixed data, so that we can rehearse the knowledge from the past using the memorized data. And of course, you can find, you can see as belonging to this section also all the methods that are concerned with the generation somehow of patterns that can be used for rehearsal, or you can consider it a 4 categories per se. So in the hands-on session, we are going to try to address and implement 2 different methods. So the first one is the pure rehearsal approach, in which we just, I guess it's not a real continual learning approach, but you just store all the data that you encounter up to a certain point, and then you mix all these data together, and you fine-tune the model over time with all these data. So it's not really scalable and efficient solution, but it's working quite well. And then we are going to try to implement a very famous strategy, which is called elastic weight consolidation, and was proposed in 2016 by DeepMind. And I think that it's worth now explaining a bit more in depth these strategies, since we are going to implement that, try to be as intuitive as possible. So essentially, let's say that we have a neural network that you can see on the left here. It can be an MLP, it can be a component, whatever. But essentially, what we are doing here, being AWC, elastic weight consolidation, regularization method, is trying to add a regularization term to the loss function, so that then we can preserve the weights that are important for the previous data distributions and previous tasks, right? So I hope you can see my pointer. I guess so. So essentially, when we encounter a new task, and we define the loss function, as Kevin's explained in his lecture, we want to define somehow the loss function as a entropy loss function or a different one. But then we can add this loss function with a plus term, this regularization term, that is controlled somehow at this parameter lambda. And with the idea, as I was saying before, of disincentivate changes in the weights that are important for the past. So how we can do that? Essentially, this summation is across the OK parameters that we have in your network. And then what we do is saying, okay, we have this optimal parameter theta k bar that we have already learned from the past, that it's okay to model the previous data distributions already. Then we are saying how far we are moving is the weight to suit the new data distribution, so that we are currently tuning this weight theta k to to suit the new data distribution of the new task. And then we are saying how far we are going with this differentiation. We are saying how far we are moving essentially that weight from the optimal one of the past. So this tells us somehow how much we are changing each parameter, right? And then we are gonna multiply this term with an importance term. This is omega k nu, that is the importance of each weight for the past, for the previous data distributions and tasks. So essentially, if the importance is I, and we are changing that parameter a lot, so that this differentiation is growing, then all these term is going to be, of course, for a number of parameters, is going to be large, and then this behavior is going to be disincentivized, right? So that's the whole idea of elastic weight consolidation. And the only part that is interesting, I mean, and mainly to be explained, is how we can get the importance of each weight at the end of a training procedure. And there are a lot of ways you can do that, but for AWC, the importance of each weight is based on the notion of the Fisher information. I'm not going to go into details, but essentially is the amount of information a particular parameter is carrying about a particular data distribution, and you can somehow approximate it with the variance of the gradient with a sample of the training data or the whole training data, and we're going to see how we can do this. Don't worry, in the hands-on session, more in details with the code. So I think we are now ready with this, after this brief introduction, to move to these practical sessions. So at this point, you have three ways of following the lecture. So the first one is just to watch working on the notebook. So just following this stream. And then the second option is to click on this link that you can see on the bottom of, maybe you can't, but on the bottom of this slide. And you'll find this link, maybe we can watch together. This is the AI for People organization on GitHub, and you can find all the material of the workshop on this repo, first AI for People workshop. Thanks, Phil and Kevin and all the others who already set it up. And essentially, inside the Continual AI directory, you can find both the slides that we are watching now, as well as the notebook I've been preparing for you. And you can click on it, and you can see here essentially the notebook with the cells that already been computed by me this morning. And you can see the results, and you can watch and follow with your own pace. While you listen to me, you can see all the code and study it as well as the results. So this is another option. Otherwise, you can also, while you hear my voice, you can also open your notebook on Google Colab and play with it yourself. So I'm going to do that. You can follow these steps as well, but this is nothing new with respect to what you have already seen with the Kevin's lecture. So essentially, we're going to go to Google Colab. Right. Then we go on this tab, GitHub, and then we can write here AI for People. Git. And all right, we have already the repository. It's already the right one. So first AI for People workshop, and here we can find on the master branch all the different notebooks that have been made available. So for our current session, we are interested in this one. So Intro to Continual Learning. We can click on this, and so we are now into the Google Colab. I hope you're familiar with this UI, but it's nothing that much fancy. Essentially, you can see here on the left the table of content we're going to address, and then you can see, for example, here the button to connect to the virtual machine that Google is generally offering us for free. So it is initializing. You can check the runtime here, runtime. So essentially the background, our background we are going to use is change runtime, and yeah, we are going to use the GPU, but even a CPU will be fine. We'll be using a MNIST, the MNIST dataset you already seen. Well, you can see here maybe the resources that we have now. So we have like 12 gigabytes of RAM and more than 30 gigabytes of disk that we can use. That's more than enough. So, all right, I think you are all set up. Maybe I can make a little break here, and I can ask you if you have some questions about the introductions that I made before about continual learning, and also if you are all set up with the Google Colab, and we can proceed. Let me know if you have any issues. You can find the links, or you want sometimes to set up the environment. Okay, yeah, I can see that Kevin already pointed out the right link for the Google Colab. Okay, Ronaldi said, can you explain the AWC algorithm in a bit more detail? I think that maybe we can wait till we see the exact code to essentially implement it. And then if you have still more questions, we can go back to it and we can explain it even better. Okay, great. Yeah, because I think the code talks by itself, I guess, even better than myself. All right, I guess we are all set up. No one has complaints, so we can proceed. So essentially, we're gonna, in these 40 to 60 minutes and some session, we are gonna do the following. So first of all, we are gonna install PyTorch on this virtual machine. We're gonna use PyTorch 1.6, which is the latest stable version of PyTorch. Actually, the code that you can see here was made for the 0.4, PyTorch API. So don't worry if you find something that seems a bit weird, but essentially it seems that all is working and the API has not changed much from that version. So we are going to be fine. I tested this before. Then after setting up our environment, we're going to load the MNIST dataset that you have already seen before. And essentially, what we will do is to just train a simple neural network to classify the digits, just to make sure everyone are on board with that. And after we have done this preliminary, let's say, work, we will try to implement these three different strategies: the naive strategy, or just continue back propagation over time, when we have a number of tasks. And these tasks, by the way, are going to be based on MNIST, and the benchmark will be, let's say, the permuted MNIST, in which each different task is based on the idea of permuting MNIST with a fixed permutation, but we're gonna get to that. Then we're gonna try to implement the re-Arshel strategy that we have described before, and as well as the elastic way consolidation strategy. Then again, we are gonna plot the results just to see that everything was as we expected. All right, so let's go. All right, so essentially, I have already prepared, just to be a bit more quick, all the code in this notebook, and so we are gonna just maybe make a few changes, but essentially run the blocks that are already here. So even if you don't want to, code it, you can start a Colab and you can just run it cell by cell, and everything is gonna be fine. All right, so before that, let me just for more clarity remove all the pre-computed cells. So it was edit and then clear or output. Okay. So essentially in Colab, you can also run shell bash commands if you're familiar with the bash terminal in Linux or Mac. And you can run these commands using this bang syntax. So you just use the exclamation point followed by your command, and you can use like essentially the shell of this virtual machine. So in this case, just to see everything is in place here as in terms of hardware, we can run the free command, the df command, and NVIDIA SMI command. And the first one is going to tell you how much free RAM we have. The second one, the talk is about the disk, and the third one will be about checking out the hardware for the GPU. NVIDIA hardware. So okay, I think it's cool. We have 10 gigabytes of free RAM and kind of 43 gigabytes of disk that are free, and then we can use a Tesla T4 for this run. Maybe if you are running this as well, you will find that this different GPU, or maybe no GPU. Sometimes it happens. But no worries, whatever hardware you have, you'll be able to follow through these notebook, since all the computations are very quick. All right, then of course for all these sections, I have pick a few questions that will help you somehow go deeper into this lecture by yourself and find your answer, maybe with some tips here. uh, and these are interesting, and important to you if you want to execute again this notebook maybe by yourself later on, or you're very fast and you want to somehow go deeper while the others are catching up, and are all questions that are useful for to think more about what we're doing, right? Okay, so let's start by installing PyTorch 1.6. This is the command to install Torch and Torch Vision, the two main package we're going to use today. Of course, I put these numbers here of the version just for reproducibility of this notebook, but essentially since the latest Torch stable version is 1.6, you can just remove them. These are not useful, and just pip install Torch and Torch Vision, and you'll be fine. Okay, let's install Torch. Should be quick. It's much improved from the past. And yeah, we can see if Torch was installed correctly by importing Torch and then checking out if Torch CUDA is available. So to see if we have the GPU version installed correctly and if we can see the actual device. Okay, it took more than expected, but it works. Then we can import all the different libraries and modules that we're gonna need later on about Torch. So the basic Torch package, then the NNN submodule, then datasets, transforms, the optimizer, the functional submodule, as well as the NumPy and matplotlib package. And I hope you're, yeah, I mean, you don't need to know all these things. I hope just that you have an idea of them, especially after the Kevin's lecture. But you know, if you have any question, you can always write. I found a way to see the chat as well through my live phone. Okay, so let's now focus on getting the data, right? So we're going to use the MNIST, as we were saying before, 60,000 images, grayscale images, 28 by 28. And for simplicity, in this case, we're not going to use the download utils provided by PyTorch, but just these particular code base, very simple code base that Continual AI made available with the collab project that they have. We're gonna just git clone this repo and then initialize the MNIST dataset. So essentially, this MNIST class from this code base is automatically downloading the data for you and then giving you the possibility to load directly the NumPy tensor. So this is something that we would like to do for simplicity. And so in the end, with this load function, what you get here is the images and labels, xtrain and ttrain, for the training set, and then the xtest and ttest images and labels for the test set. Okay, so we have just eight different NumPy tensors of these dimensions. Sorry, 4 of them, and so you can check the dimensions here. It's 60,000 images divided with them. Of course, with one channel here, it means it's grayscale images. And then for the labels, you have just 60,000 unsigned integer. And the same for the set, which is a bit more smaller, with just 10,000 images and 10,000 labels. Okay, right. I think that this is clear enough. Then just for making sure that all is good, we can always visualize some of the items of this data set. Well, maybe I didn't actually disable this. All right. All right, so we can see that we are watching the first somehow, yeah, I mean, the first four images of the training set. It seems that these images are already shuffled, so we can see that we are now seeing 4 written digits, 0419, and so we don't need to shuffle the training set before training. And now we can move directly to the setting of torch. So we are gonna define this variable, use CUDA, so that we can decide directly which device to use based on the hardware availability. So use CUDA is gonna be what we defined before, but also only true if CUDA is actually available. And then the device in the end is going to be set up to CUDA or CPU based on that variable. And in this way, we can, I would say, decide what to use based on this parameter directly and the availability of the hardware availability. And then we also set up here the seed for reproducibility. You can choose whatever seed you want, but these in case is one. And then always forget to execute the code. All right, and then we can define our neural network this way. So we are gonna define a class in PyTorch with inheritance from an module class, and then we can define just the init method with the different layers and parameters we are going to use in the neural network. So in this case, we are just defining two comp layers, a dropout layer here, and two fully connected layers at the end. So one is the hidden layer at C1 with 320 units, sorry, so 50 units, and the output layer here with 10 units as the number of classes we want to classify in our classification problems, right? The different digits. So what's the difference between X train and T train? Is it a temporary copy? I think that Kevin already answered that. So essentially, you said X train and T train. No, X train are the images, while T train are the labels for these images. Okay, right. Kevin already answered that. Again, just for getting more clarity, here when we load the data set, we load in two different tensors, the images and the labels for the training set, and the images and the labels for the test set. You can also, in case you have any doubt, you can watch the dimensions of these, the shapes of these tensors. And you can see that for T, that stands for targets. Maybe Y should be better, but there is a dimension of just 60,000 or 10,000, depending if it's the train or test set. Essentially, these are just integer values corresponding to the classes of the corresponding images in the same position. And it's going to be a number between 0 and 9. Yeah. All right, so let's define this class that is called net with a lot of fancy. And now let's try to define two different functions. One is called train function. The second one is called test function. I think Kevin did kind of the same. I'm not sure, but they are essentially here defined to loop across the dataset for a single epoch. So essentially, we are navigating across the mini batches of the training and test set with a fix, in this case, mini batch sites with a batch number here, 256. So what we do is always the same. Every time we loop over the mini batches, we're always doing the same. We define these two different numbers, a start and end index, and then we use them to splice for simplicity. In this case, the NumPy tensor. So we get this slice of the tens of the images, and these lies for the corresponding labels, and we convert them in torch tensors, right? Because torch gets only tensors, and tensors defined in torch, and then we move these tensors to the correct device explicitly, as we defined before, if you remember here, right? And after we have somehow created a mini batch, converted the two torch tensors and moved them to the device, we can start with the optimization of this mini batch. So we reset the gradient, them to 0. Then we collect the output of the model. Then we get the loss using this, in this case, this function, entropy loss, defined inside the function module. And then we backpropagate the loss so that all the parameters into our potential module as now field gradient. And then we use this optimizer step to actually operate the optimization step, updating the weights after I mean, the autograd system in PyTorch has taken care of computing the gradient. So then we just print the epoch that we got through this function, and the epoch number, and then essentially we plot the loss over time during in the train function. Then for the test set, I mean, it's quite the same. The only maybe difference is that we set the model in eval so that every layer is notified to change its behavior if it has different behaviors for training and test, and can change its computation accordingly. Then another difference is that we shut down the autograd engine in Torch with this function, I mean, this scope of this command torch.nograd. So without the grad, we just computing in forward the forward computation of our computational graph. And so we do the same here as the test function. We navigate through all possible mini batches one time, of course, defining the start and then the indexes, and then we collect, of course, the tensors and we move them to the correct device. We compute the output from the model, and in this case, we also collect the test loss just for printing, and then the predictions, and in the end, also the number of correct predictions. Somehow then for somehow printing the final accuracy at the end of the training. Okay, so I have already defined these functions. Then for the first training of our neural network on the MNIST, classic MNIST training set and data set, we have to define a model this way. So we define this variable model, instantiating our class net, and then moving it to the correct device. Then also we set up the optimizer, in this case using the SGD classic optimizer. I think that Kevin used Adam in his presentation. In this case, we're just using a plain, simple stochastic gradient descent optimization process using this class SGD and passing to it the parameters we'd like to optimize. Then the learning rate 0.01 and momentum 0.9. It's pretty much standard. Of course, you can find better parameterizations, but for the sake of this tutorial, we're gonna stick to this hyperparameterization. Then what I why I made these different two functions, train and test, so that we can have an explicit let's say, training here with just a couple of lines of code and deciding here the number of epochs through which we're going to go through. In this case, just 2 epochs in which we, for every epoch, we train the model on the entire training set, going through all the possible mini batches, and also one time we test the model. We test the model for each epoch. So let's see if everything is working and is in place. All right, so it just finished. We can see here that the loss function is going down, so that's great. And also that the accuracy is growing across the epochs, so from 90% to 94%, and the task is pretty much solved. I mean, we are happy with, let's say we are happy with this accuracy. So this was the first stepping stone for our tutorial. And if you have any questions now, it will be a nice time to stop and to get those questions out of the way so that we can move to the second part of the tutorial. Kevin said, you set your model to train mode again in the train function. I'm not sure. Probably, yeah. Okay, yes, we have the right call here. I mean, in this case, thanks, Kevin, by the way. And yeah, I mean, in our case, I think the only layer that is going to be affected by this is the dropout here. I think that the default probably the default parameter is at 0.5. I don't know if it should be disabled during test phase. But this is the only layer that is going to be affected. But it's cool to every time you want to train a model to set it up in train mode, and every time you want to test it in eval mode. Yeah. Sometimes I forget. I think it's nice that the PyTorch has the right level, I think, of complexity for the API, in which you can change things and understand things the right way. But at the same time, sometimes they are quite low level. For example, doing this or clearing the gradients explicitly, it somehow can be daunting sometimes when you forget to add them. All right, so where we were, okay, here. So all right, I think that everyone are now able to train your model on a MNIST. So we can move to the let's say continual learning setting a scenario definition. So what we're gonna do? So essentially, we're going to create 3 different tasks. The first one is going to be the MNIST basic task and data set. The second one is going to be a fixed permutation of the images of the MNIST data set. And the third one is going to be another permutation, another fixed permutation of the data. So essentially, we are changing the order of the pixels within each images, but with a fixed reordering of that, and that's allow us to create a very different data distribution with kind of the same complexity. And even though we as humans, we are not really able to see the patterns in this data, for a machine, it's kind of the same complexity as the first basic MNIST task, the natural one. The only thing that changes is that we are actually disrupting the 2D positioning inside an image. So destroying that has an impact on the complexity of the problem, but let's say that we can approximate the complexity of all these different tasks, and we are changing the distribution so much that you will see it's going to be difficult for our model, even though it's been trained on the first task, the MNIST task, to generalize to those different settings. And so this gives us the possibility of working in a very simple settings, a scenario, but with different tasks in a continual learning setting. So what we're gonna do here is to define the function permute MNIST that takes as input the MNIST dataset, train and test, and then with a particular seed, and then defines this particular fixed permutation we are going to use, for changing the order of the pixels for each image. So essentially, what we do is the following. So we set the random seed of the NumPy package, and then what we do is to create a random permutation with this permuted index using the shuffle function of this list. So we shuffle the order of these indices. And then what we do is to flat each image of each set in the MNIST dataset, training dataset, and then essentially permute the indexes this way using a shape function and this sliding operator. I think that I run that. Okay, so then having defined the permuted MNIST function, we can use it just this way. So passing as a list the xtrain and xtest tensors, and then, for example, in this case, setting the seed to 0. And we can get just two different tensors for the xtrain 2, let's say for test 2, and xtest 2 tensors. So again, pay attention here that we are just permuting the pixels for the images of the train and test set. So we're not changing the labels because the labels are not important. In this case, we are just changing the input, let's say, distributions for these tasks. We're going to have always 10 different digits to classify. And of course, we need to do that both for the training and test set. So for each task, we maintain both the images of the training set and the test set coherent among each other. All right. So we have done the permutation, and we are gonna see now and plot the results of this permutation on a simple image. In this case, 0 and digit. So what we are showing in the first image is this particular image. All right, and then in this case is another image in the xtrain 2 tensor. So as you can see, I mean, it seems much more difficult for a human to try to recognize digits. In fact, I don't know. It should be like the same number, but it's quite difficult to recognize it. And but again, apart from this, representation of the image, it should have the same complexity, kind of the same complexity. So now, since we have already trained our model and it is now in this variable, we can try to test the model performance on the xtest, t-test test set. So the first task test set. And then also testing it on the second task test set to see how this model that has been trained on the first task can work on the second task, right, on the permuted task. And you can see here that the network maintains pretty much the same level of accuracy, of course, as before, 94%. On the first task, but is not able to generalize to this new data distribution that still contains the same information content, but in a different ways, of course, and it's another distribution, let's say, encoding these digits. And so the network, since it has not seen these data before, is not able to generalize to that. So this is just a fast check to see that these data distributions are quite different, and it's difficult for a network to generalize directly on this task without seeing any training example. So we have a question from Mohammed. Why are shuffling pixels? So the idea is that we want a number of tasks, training sets, training batch, different splits from which we can learn from over time, right? This is a continual learning settings we want to operate in. So the idea is to create different input distributions for the same task so that we can try to learn to generalize across all of them while we learn over time. And so this is one of the simplest way researchers have decided to, I mean, it's one of the simplest way to define a continual learning setting, starting from a simple bench chart. It's something that researchers have been proposing and using also very much in the past. So this is why we are shuffling pixels. But you can also define different tasks, for example, by rotating these images, for example. And that's also a way to change the data distributions and create different batches of data and try to generalize of the same concept from different data distributions and variation of the same task. Okay, so the basic, the basic approach that we will take at this point is saying, okay, we want to be able to generalize across these two tasks. Well, what about we just fine tune the network we have been training on the first task to improve the recognition? I mean, to learn about these new data distributions and let's see what happens. And so this is what we are going to do. So with the same model that again has been trained on the first task, the standardized images. What we try to do is to fine tuning with an epoch, two epoch in this case, on the X train 2 dataset, so the permuted one, and then we test it every epoch and we see what happens. All right, so the test is always on the second task. So we can see that after one epoch and two epochs, it can reach like a lower level of accuracy, as we were saying before, with respect to the task one, but it still happens to be able to recognize these digits even in that permuted form without 83% of accuracy. So we're now able to recognize well these digits into the second task, the permitted task. But here, what we do is to test on both the first task test set and the second task test set. And you can see that while on the second task test set, we can achieve, as we have seen before, an 83% of accuracy, we are now not able anymore to recognize the digits in the standard MNIST data distribution. So this is exactly what we've been talking about before. So the phenomenon where we have described as the catastrophic forgetting. So the idea that as soon as you learn about a new data distribution, that if you don't do anything, you just learn from these new data, then you completely erase the information encoded in the weights with respect to the previous data distribution, and we are not able to solve that task and to model the data distribution anymore. Right, so is everything clear? Are there any more questions up to this point? Marcello is asking, what if you shuffle only the data of few categories? Will the forgetting affect all the categories? No, I think it won't affect the other categories. And yeah, exactly. So if you don't modify the original patterns for these categories, you won't have forgetting from those. But it's right that it may help taming somehow forgetting, because you, especially in more complex problems that I missed, the network should be able to, at least at the feature extraction level, being able to model both distributions. So maybe it may impact on and reduce forgetting in that sense. So now we have somehow understood the problem of catastrophic forgetting in practice, and in this particular scenario of just two tasks. For the sake of continual learning and the algorithms we're going to implement, we are just going to add another task with another different permutation. So essentially, the scenario we are going to address is based on three tasks, in which the first one is the standard MNI task. The second one is based on a permutation with this seed one, and the third one is based on a permutation with the seed2, so a very different fixed permutation. And essentially for each of those tasks, I define a list of tensors in which I have a tuple, two tuples. The first one is the training set, and the second one is the test set. And then for each of those tasks, what I define is another list collecting those. So essentially, I have a list of tasks, and each of those tasks have both the training and test set tensors. All right. Just because now we are gonna try to learn those tasks and these batches of data over time in a single iterative procedure. And we're gonna do that with three different strategies, as we were saying before: the naive strategy, the rehearsal strategy, and the elastic way consolidation strategy. For the naive strategy, what we do is to just reset the model and the optimizer. So we just instantiate another model here with the same class we have defined before, and another optimizer with the same parameters. Then, after we have done that, we can define our main procedure that is just going to add this loop over the tasks, right? Over these different training sets with different permutations. And essentially what we do here is to take from the task, the tuple that interests us, in this case, the training tuple, xtrain and ttrain. And then we're going to use the basic train function we have defined before to train the model on this data. And then just one epoch in this case. And then after that, we're going to just test the accuracy for this task as well as the other ones, right? Yeah. All right, and so let's check it out. Right, so here you can see we are navigating through the tasks. So task 0, and then for this task, well, we just one epoch just for simplicity here. We reach 90% accuracy on the first task. This is just the testing session here. On the first task, so this is reasonable because we have just trained the model on the first task, and as we have seen before, is not able to generalize to these other two tasks with a 5% and 11% accuracy respectively. Then automatically with the same model, we move to the in a continual way to the second task, training on task 1. And again, after we have finished just an epoch on this one, what happens is what we expect, the forgetting phenomenon, which we forget to solve the previous task. We are now able to somehow solve the second task, but again, we are not able to generalize to the third task. We are not encountered yet. And then for the third task, again, we are not able to solve the previous two tasks anymore, almost, and we now instead have a we are kind of able to solve the third task with a 62%. So this is what we expected, and so it just to somehow understand what's our baseline, basic baseline, and IV baseline for the task. We would like to now overcome with better strategies. Right, so one of the basic and more simple ideas for, in the end, having a single model that can solve all tasks that it has encountered in a sequence is to use a rehearsal. That is simply keeping track and collecting, memorizing all the data we have encountered before, and just every time retraining the model on all these data. So to do that, we are going to use also an additional function that we define in shuffle in unison, in which, I mean, you can implement this in many ways, but essentially is based on the idea of shuffling different sets in the same order, right? We would like to shuffle both the images and the labels in the same position, in the same way. So we're not going to go into details about this shuffling unison function. I've seen that we are quite late, but just keep in mind that this is a function that simply shuffle dataset comprising different tensors in it. So we just define it. We reset also the model and the optimizer. And then the function that we have seen before, navigating through the different the tasks, it just changed in this part. So essentially, we collect the training data for the task. And then what we do is for each of the previous tasks, we concatenate somehow their training set to the current one, so that we have a concatenation of all the previous data sets and the current one. And then what we do is to shuffle this entire training set that is now containing to X train and T train, and then shuffle that in unison. And so we have a single big training set with all the different previous training sets for all the tasks we have encountered before. And then we simply train on this big fat training set. And then we test it as before. So let's see how it performs. So again, it starts with an high accuracy on the first task, very low on the other tasks. Then it can somehow maintain and I guess even improve the performance on the previous task. And the same happens in the third task, where we can maintain on a very high level accuracy performance on all the three tasks. So that's very interesting, and it's cool from a accuracy perspective, but at the same time, it's quite not scalable, right? Because we have to maintain all the data we have encountered before. And not only that, we have also a massive computational overhead, because we are retraining every time on things we have already learned in the past. So this is not really scalable, and it's growing at least linearly with respect to the number of tasks we process, and that's not really what we want, right? So this is where why we define now different solutions for continual learning. For example, the AWC strategy. So for this strategy, we're going to use these three different new variables. In this dictionary, Fisher, we're going to put inside the Fisher information, the importance of each weight. In the second one, we're going to store the optimal parameters for each task. So the best parameter we could learn from the current data distribution. And this is the lambda term we have seen in the formula, trying to control the localization term, and is set to 0.5. And again, we reset the model and the optimizer. All right, and then we need to define now another method that is called on-task update. We are going to call at the end of the training after each task. And so what we do at the end of the training is to just, for Marcello, he's asking, I missed what Fisher is. Sorry, this variable is essentially the Fisher information, also known as the importance of the weight at the end of each training, of the training of each task. And so we are going to store for each task the importance of each weight. And so essentially, this is why we define the on-task update function here. At the end of the training, we do just that. So we accumulated the gradients going through all the a sample set or the entire training set, as we will do in this session. And we, as always, we pick up all the mini batches here, and we just do the same as we just backpropagate the results, so that now in every gradient attribute inside our parameters, we can find the gradient. So what we do is to just create another dictionary for each of these dictionaries, and that is going to be for each task, so that we can now load into these different dictionaries for each parameter both the optimal weight, so the content of the weight, as well as the weight importance. So here, as I was saying, the Fisher information can be approximate as the variance of the gradient on a sample set. And since the mean expected mean for a parameter is 0, then in this case, the variance can be computed just by squaring the gradient of each parameter. So we collect these importance estimate inside the Fisher as we were saying. Oops, sorry, did I execute it? Okay, now we have defined the function, and for the sake of clarity, we're also gonna change the train function we had defined before with this train underscore AWC function, which is going to do exactly the same, but just with this piece of code, additional piece of code. So it's gonna go through the different mini batches of the training set. Then we're going to compute the loss, but before backpropagating this loss, the simple cross entropy loss, we're going to add the regularization term, right? We have explained in the previous slide. And so essentially what we do is to recover the importance of the weight and the optimal weight for each of the previous tasks, right? And each, of course, of the parameters. Remember the summation across the k parameters. And then what we do is to add to the loss the regularization term with the lambda term here, and then the difference between the optimal weight and the current weight squared, and then times the importance of that weight. Then we sum all over this and we add it to the loss, right? And then we optimize it with a backward step. Okay, Kevin is asking, where do we call here the previously defined functions? I guess the previously defined function is referred to the on task update. So we're gonna see where we call it. But this is, I think that it's out of this loop because, let's see. Here we go. So essentially, again, we go through the different tasks as always, but instead of calling the train function for each epoch, we call the train AWC function. This is why we call it outside, because this function was made to go through the training set just for one epoch, and maybe we want to do it for more than one epoch. And we want instead to compute the importance weight at the end of an entire training on that particular training set of the relative task. And great. So in this case, exactly, we run it for 2 epochs, and then we compute the importance of each weight, and we collect the optimal weights using the function on task update. Perfect. And keep in mind that yeah, for the first task, essentially we are not adding the regularization term, because in this case this is not computed. There's no previous task. And all right, so I think we can run it. Okay, so as always, it starts with a reasonable accuracy on the first task, not really generalizing to the other ones. Then is somehow in the middle with respect to the naive and full rehearsal strategy. It can retain a bit of knowledge about the past and still learn about the second task, and as well do the same for the next the third last task. So this is pretty much it, and we can plot the results if you can see that, if they're somehow working. Okay, right. So we can see here what we were saying before. The naive strategy is kind of flat, while the full rehearsal strategy is growing steady across the tasks. It can generalize across all of them at the end of the entire training procedure, while the AWC version here is kind of in the middle, improving with respect to the naive one, but still far away from the rehearsal strategy. So that's why continual learning is being investigated over the past a lot. It's quite an interesting topic, and there's a lot, I mean, a huge space of improvement still. So I think that we ended this Ansel session. If you have any questions about this, you can ask it now. So again, in case you want to play with this notebook, you have not already, you can find it directly on the Google Colab, entering on the GitHub tab our, let's say, code name AI for People dash Git, and you will find the notebook to play with directly. And I think we don't have time now to go through the other slides. Okay, so we have one general questions. One general question: what is the difference between continual AI and online learning? So over the past, we have seen like I mean the history going in circles, and there's been a lot of interest in the past about incremental learning, online learning, lifelong learning as well, and it's so of course as you may know if you're doing research. There are different communities having slightly different objectives, as well as using a different nomenclature, and of course, many of the topics that have been addressed by these communities are shared and should be even more, I mean, shared and understood together. But this is just a matter of slightly different interpretations and interests by these group of peoples over time, of course, over the history of computer science. But for now, it seems that continual learning is one of the biggest, let's say, community that works specifically within the deep learning community, and using almost only neural networks and gradient-based architectures. So this is pretty much the focus that many researchers have been working on. But of course, there are many things that they share with other communities, maybe historical bigger communities like the lifelong learning, I mean, incremental learning community. So it's lots of workshop, so open end. So right, so do you have any more questions, like more general questions as well? Let's go back to these slides. I'm sorry they couldn't go over the more general topics that I have been preparing here for you. But I hope you enjoyed these. I hope you enjoyed this last section and the entire workshop as well. We have a question from Marcello. Yeah, if you keep on adding new tasks, will AWC start forgetting eventually? Well, it seems that, yeah, it's elastic wave consolidation, at least, it's kind of prone to saturation. For so depending on the, I mean, the strongness of your lambda function, your regularization term, then what you end up doing is that or forcing and freezing all the weight so that you can't learn new task, or the opposite, in the maybe forgetting about the previous distribution. So it's not really, it seems to be at least not really so much scalable, and so that's an interesting research question that we as a community address, and we are addressing. So we have a message here from Sobia. Thanks for the whole team of AI for People. It's a very informative workshop. We'll wait for a interesting workshop. Maybe you will also try to conduct something on bio-inspired computation as well. Well, at least from the continual learning aspects, I mean, that's very interesting and important, and it would be nice to integrate future workshops with visions from the biological worlds. That would be nice as well. I guess it's very important for the future of AI in general. Kevin, sorry, I did not mean communities. I mean training a neural network on a single task with new data for that task. Oh. Okay, in a single task with new data for that task. So basically, when retraining the whole model, yeah, of course. Again, the nomenclature is not really clear. I mean, online learning has been used in the past with different interpretations. So, for example, one of the latest interpretations that online, in the sense that you just process one piece of data at a time, so one example at a time. So in your case, I mean, the whole continual learning community is trying to not storing data at all from the previous task. So in that sense, they are quite the same. Exactly. So without retraining the whole model from scratch. Yeah. Okay. Gabriele asked, answered also the another question from Marcello, and then okay, great. So I guess we have answered much of the questions, and we are pretty much on time. So again, thank you for joining. Not just this uh, lecture, but all the talks and previous lectures for this first AI for People workshop. Of course, I mean, AI for People is a nonprofit research organization, and the financial backbone of these activities are the donations. So if you're willing to even buy us as a coffee, that would be great. It would be super important to us. So consider making a donation following the link below at the bottom of the slide. So thank you again for joining, and I hope to see you for the next workshop. Thank you. Bye.